Let's do two more examples where we want to find the Laplace transform of a function. First, find the Laplace transform of the function f of t equals e to the power at, where a is a constant. So we're asked to find the Laplace transform of e to the power at, which is a function of s. And by definition, this is the indefinite integral from 0 to infinity of e to the power negative st, and then we're multiplying that by f of t, which is e to the power at, and then dt. So first of all, let's use a limit because we have an indefinite integral. So this is the limit of n goes to infinity of the integral from 0 to n. And then what we can do is we can simplify this, because if we multiply these powers of e, we can add the exponents. So I can write this integral as e to the power negative st plus at, and then I'll factor out a t. So I get e to the power a minus s times t. So what I use there is e to the power a times e to the power b is e to the power a plus b to get that new exponent there. Okay, so this now is equal to the limit as n goes to infinity of antiderivative of this will contain e to the power a minus s t, but then we have to divide by what's in front of the t. So we have 1 over a minus s times e to the power a minus s times t. If you don't see that, you could also find an antiderivative using substitution here. So we have to plug in n, and we have to plug in 0. And so this is equal to limit as n goes to infinity of, and we'll only have to worry about the limit for the first part, because the second part we're not plugging in an n. So we get limit as n goes to infinity of 1 over a minus s times e to the power a minus s, and then times n. And then we're subtracting 1 over a minus s times e to the power a minus s times 0. Okay, now when you plug in 0 here, this term becomes 1. So our second part of this expression is just minus 1 over a minus s. So now, what happens to this first part? Well, if this is positive and n is positive, then this goes to positive infinity when n goes to infinity. And that means that this e value blows up and it does not have, the limit does not exist, or the limit is infinity. So what we need to have is that a minus s is less than 0, because if you multiply negative times a positive, you get a negative value here, and e to a very large negative number, that approaches 0. And real quick, remember that when you look at e to the power x or e to the power t, whatever your variable is, if you plug in a really large negative number, the exponential function tends to 0. So this first value is 0, and that is if a minus s is greater than 0. And then we have 0 minus 1 over a minus s. And then we can clean that up a little bit. If we multiply top and bottom, let's say we put the negative in front of the 1 and then multiply top and bottom by negative 1, you see that we can write this as 1 over s minus a. So all I did is incorporate that negative into the denominator, and so I get a positive value here. And if we solve this for s, we can show that, oh, I'm sorry, this should be less than 0. So I just argued that if this is less than 0, then this is very large negative and it tends to 0. So if a minus s is less than 0, this goes to 0. And if you solve that for s, that inequality, this holds if s is greater than a. So that is the Laplace transform of our function e to the power at, and it only is valid as long as s is greater than a. Okay, let's do one more example here for the Laplace transform. Let's use a piecewise defined function. So the function f of t is defined as 2 on the interval from 0 to 5. It's 0 on the interval from 5 to 10. And then it's e to the power 4t when t is greater than 10. So now let's take a look at what the Laplace transform is for this piecewise defined function. So we take the Laplace transform of f of t, and it will be a function of s. And what we'll have to do is, when we look at the indefinite integral that would normally go from 0 to infinity, right? It's 0 to infinity, and then e to the power negative s t, and then f of t. dt. we will have to split up the integral from 0 to infinity into 3 pieces. And we know from calculus that if you take an integral from a to b of f of t dt plus the integral from b to c of f of t dt, then that's the integral from a to c of f of t dt. So that's the idea behind this. So we're going to split this up into integrals from 0 to 5, right? So the first part of the function is defined as 2 on the interval from 0 to 5. So our function is negative e to the power st times 2, right? Our function's defined to be 2 on that interval. So we put 2 there, and then dt. And then the second part of the integral goes from 5 to 10. And the function there is 0. So that's really nice because that's going to simplify things a lot, because we'll just have an integral of the 0 function. So then that's dt. And then finally, the last part is when t is greater than 10. So that's from 10 to infinity. And then we have to multiply that by e to the power negative st times e to the power 4t dt. Okay, now the first two integrals are just regular definite integrals. So we can take a look at what is the antiderivative of that first function, and that will be negative 2 over s times e to the power negative st. And then we have to evaluate that at the values 0 and 5. Now, for the second part, this function simplifies to just 0. And when you take a definite integral of the constant function 0, you end up with 0. Just think about it. The definite integral is the area under the graph. And when your graph is the function that's identically equal to 0, there is no area under your graph. So that's 0. Okay, and then the last part, that's an indefinite integral. So we'll have to introduce our n goes to infinity limit. And then we take the antiderivative of this function, and we're going to apply that same trick we did in the previous problem, where we're combining those two exponential functions, and we'll get that this function is e to the power 4 minus s times t. And that is just this function here. And in order to get the correct antiderivative, we have to divide by 1 over 4 minus s. And then we have to evaluate that at n. And now, important here, don't put in 0 here. We want to put in 10 because we had to split up the integral. And so that is the major difference with what we did in the previous example. So now the first part is just plugging in numbers. So negative 2 over s e to the power negative. And now we still have to think that t is our variable and s is our constant in terms of the integral. So we get negative s and then times 5. And you see I use these little extra notches on my s because otherwise my s's and 5s I can get mixed up there. So I plug in 5 and then I have to subtract the expression when I plug in 0. So minus 2 over s and then e to the power negative s times 0. And that part is just 1. And then plus 0, don't have to worry about that. And so now I get the limit as n goes to infinity of 1 over 4 minus s, and then e to the power 4 minus s times n. And that's the only n I will have. And then I subtract from that 1 over 4 minus s e to the power 4 minus s times 10. Okay, now we're going to see what happens with this limit. And again, we know that n goes to positive infinity. So if this part here is less than 0, that limit will be 0. So if 4 minus s is less than 0, this limit is 0. Okay, and now let's just clean this up a little bit. So our first part here is negative 2 over s e to the power negative 5s. And then minus minus becomes plus 2 over s. And then plus 0. And then minus 1 over 4 minus s. E to the power, and now let's just multiply that out, 40 minus 10s. And we can solve that for s, and that's if s is greater than 4. So let's put it all together. So this is 2 over S minus 2 over S e to the power negative 5S minus 1 over, or we can make that into 1 plus S minus 4 e to the power 40 minus 10S. And that's if S is greater than 4. And that is our final answer. Now, we'll conclude this video with a theorem for the Laplace transform, and it uses the linearity for integration. So let f1, and f2 be functions whose Laplace transforms exist for s greater than alpha, and let c be a constant. Then for s greater than alpha, the Laplace transform of the sum is the sum of the Laplace transforms. L of f1 plus f2 is L of f1 plus L of f2. And the Laplace transform of c times f is c times the Laplace transform of f. So I will just prove the first part, and the second part is very similar. So if I take the Laplace transform of f1 plus f2, then that is, by definition, the indefinite integral from 0 to infinity of f1 plus f2 times e to the power negative s times t dt. And I can split that up as follows. I can distribute that. And so I can write that as f1 times, so that's f1 of t, right? And then e to the power negative st, and then plus f2 of t times e to the power negative st dt. And then by linearity of the integral, I can write this as the indefinite integral from 0 to infinity of f1 of t times e to the power negative st. Right, so I have f1 of t here, dt, plus the indefinite integral of f2 of t times e to the power negative st dt. And what you'll see is that this is the Laplace transform of f1. So that's L of f1. And then plus the Laplace transform of f2. And so that proves the first part of theorem 1, and theorem the second part of theorem 1 is proven in a very similar way. We'll do some examples with this in the next video.